So this is problem number 7, and it's generic in that there's no numbers. Most of your AP exam is going to be like that. Although you're allowed a calculator, most of the work you're going to be doing is finding expressions. This particular one is not terribly complicated, but usually when you have a problem like this, you're going to be limited to the information that can be allowed in your answer. So it doesn't really state it here, but I think when you read the question, in a problem like this, when they're giving you specific information about, the situation, they're also telling you in a very real way what's allowed to be in the answer. So in this problem, m can be in the answer. They say it's moving at a constant velocity, so that's just to let us know that net force is equal to 0. They say there's a coefficient of kinetic friction of mu between the ramp and the table, and that there is a horizontal force applied to the box of, I think it was just F, right? So somebody's pushing on the box with a force F, and the whole thing is inclined at an angle of theta. All right, so your expression at the end can have F, theta, and m in it, and mu. Everything else has to be eliminated from the answer. So in the modern AP exam and on any test I give you, there'll be a statement in the first paragraph on what variables are allowed to be in your answer. So you treat those as the variables. Anything else that you introduce into the problem can't be in your answer. Everybody follow along? All right, so let's begin. Like any of these problems, I think the place you should start is a free body diagram. So in keeping with that tradition, downward force, weight. And is it becoming clear that all of these end up looking the same? For those of you who are new to this, you've noticed that every inclined plane problem ends up looking exactly the same for the most part. So the complaint that every one of these is different, I don't know what to do, is starting to fall away. It's not really legitimate anymore. Practice, it's the same every time, so start practicing. Do them over and over again until you don't make those mistakes. There's going to be an applied force. They gave it to us. It is up the ramp. We don't know the size of this force, but it has to be enough to push against the gravity that's going down the ramp and against friction. So I'm trying to make it, this is one of the forces or one of the values that can be in our answer. And there is a frictional force that should be directed down the ramp because the box is moving up the ramp. Yep.
So with the applied force, it says it's moving horizontal. Does that still
Oh, horizontal. They say it's horizontal? Yeah. All right, well, if the force is horizontal, and I guess Mr. Shelton should read more carefully, that's going to add a certain level of complication. So that's the direction of our applied force, something like that? All right. So this is actually kind of a tough one. I like it. Does that look horizontal to you guys? Horizontal enough? All right, so this has got immensely tougher. I like it. We have a choice to make. The system's not accelerating. So in order to do this question, we need to choose a coordinate system. We want to choose a coordinate system that aligns with the most number of forces possible. It's either going to be lined up with the force and weight or the normal force and friction, but it can't be aligned with both. Although those two are at right angles to each other, there's a right angle there and a right angle there, there's not a relation between them except for theta. Now, there is an advantage to making one choice versus the other. And it may not make sense which one you should choose, but you have to eliminate normal and friction in the problem. I think you might find this easier to align it with normal and friction than to align it with the force and the weight. We can try it both ways to see which one's easier. But since you have to eliminate friction and normal from your answer, and because we know friction and normal are related by mu, it might be easier to have some whole value representation of those along an axis rather than those having to appear in both the x and the y direction because you split them up into components. Now, just to have you understand, if I was to rate problems, I'd say this one is a 3 on the level of difficulty, with most of your homework being what I would suggest is a level 1 on the level of difficulty. And what's that? A 3. I would never rate anything higher than that. I don't think we can make more gradations than that. So, 2 to me is one that has some challenges, but is relatively capable of being done. 3 has some significant mathematical challenges or significant conceptual challenges. 1 is prescriptive, meaning most of the problems that you've had in your homework, if you just do the force concept inventory process, you'll get an answer to those questions. This is going to leave you with a complex thing to analyze. So I think this one's tough. And also right now, this choice that you make really dictates whether you can or cannot do this problem. So I don't generally tell you ahead of time whether they're going to be hard ones or easy ones, and I don't put them in a particular order. So I'm going to use this as my coordinate system. And I know I have a few of you that are still kind of struggling, so this is theta. All right, I put in the y one first, the one that's aligned with the normal force, so that we can identify where to put theta in our problem. But we have to put theta in 2 places. So this is the theta relative to the weight. There's going to be another place where theta is going to be, and that's theta relative to the applied force. Both of those have to be theta. Now, I want to use the same color for the coordinate system, so give me a chance to redraw that. There we go. So the y direction, I'll make this way, positive y, and this is the positive x direction. So net force in the x direction equals 0, and net force in the y direction equals 0. I'm going to have to break the weight and the applied force up into components. The weight is, again, pretty prescriptive in that we've done this a couple times before, and I'm hoping you are moving towards a situation in which you kind of got it memorized. I would encourage you to do so. This will be mg cosine theta, and this will be mg sine theta. When grading your quizzes, though, there's people who still add the weight in somewhere else. First, mg is weight. Second, when we do this process and we break it into components, we are replacing the weight that's drawn here with these 2 arrows. They now represent the weight. So the weight itself is gone once we do this. All right, everybody okay with that? Because I have a few of you whose quizzes will still have weight independent and then mg something or other somewhere else. I'm going to have to do the same thing with this applied force. So there's going to be an applied force in the x direction, that'll be F cosine theta, and an applied force in this direction, which will be F sine theta. Again, once I've done that, I'm saying that I no longer need the arrow representing F. So I'm going to get it out of there. If I can. Oops. Nope. Maybe I can't. Well, I can't get it out of there, so it's going to stay there, but imagine it's gone. So now, net force in the x, net force in the y. In the x direction, I see 3. So I see this one in the x direction, I see this one in the x direction, and I see this one in the x direction. 2 of those appear to be in the negative x direction, and 1 of those in the positive x direction. Any question about those 3? All right, so that'll be F cosine theta positive minus friction minus mg sine theta, and that equals 0. Any questions? Am I still doing a problem that is within the scope of what we've talked about in class? I agree that this one has a perturbing factor, but is it any different than what we've done yet? Now I do have to deal with the y direction, and I have that in the y direction, that in the y direction, and that in the y direction. 3 things in the y direction. 2 of them are negative and 1 of them is positive. Is that all good with you guys? All right. So in the y direction, I have normal minus mg cosine theta minus f sine theta, which 2 equals 0. All right. It's a little messy and a little busy, but that's all Newton's laws can do for us. Now, you're supposed to find F in terms of everything else and eliminate friction and normal force. So although we have used our Newton's law stuff to get us these 2 relationships, now you have to figure out what to do next to get to a problem that answers the question. That's separate, understand. This part is still prescriptive. I mean, you can just follow a series of steps to get here. I didn't say they were easy steps. And yeah, a minus sign out of place here and there and pointing an arrow wrong, that has, a tumbling effect that destroys all sorts of work here. So being careful, being precise, being cautious, taking your time. I think some of these take 15, maybe 20 minutes to complete, even if you know what you're doing and you're taking your time. So that's why I'm suggesting you budget your time for homework for stuff like this. But knowing where to go now, this might be hard. I don't know that there's a clear path, but there are probably multiple paths. I want to eliminate friction and I want to eliminate normal force. I'm allowed to have everything else in there. I'm allowed to have m, I'm allowed to have theta, I'm allowed to have g because it's considered a physical constant, so physical constants are allowed in our answer. And I want to solve it for capital F. This seems like a lot of substitution. What you don't see that I think takes practice is n and f. These are the variables for substitution. They would have to be eliminated. We're solving for f. Now, this takes practice, understanding which things can be in your answer, which things can't, and how to do elimination here. But this is 3 equations with 3 unknowns. We have to eliminate 2 of those unknowns. So I'm going to start with substitution. I'm going to solve this for normal force. Now that I solved that for normal force, I can substitute it in to get an expression for the frictional force. So I've done this first, and now I'm going to use this so I can get it in terms of friction. And then I can substitute it in, over here. Does that make sense so far? All right, so friction equals mu times the normal force, but the normal force is all of this. That's all normal force. Now, if you're taking notes and you're trying to give yourself something useful to practice, because to me, once I'm done here, this is test worthy, okay? I don't care that I said it was a 3 at the beginning. It's test worthy because once you've seen it done once, this problem is the same every time. It's hard for you the first time to do it. It should be less and less hard every subsequent time. There's only so many ways they can put these problems together. So the first thing I would probably want to have in your notes is that you're trying to do substitution to eliminate friction and normal force. And this is not the only way this can be done. It's just one way to do it. I'm doing it by slowly and deliberately solving for things I'm trying to eliminate and plugging them in other equations. That's what I'm doing. I have a plan in my head of what I want to do. I figured it would be easiest to use this first as my first level of substitution. And that's all. That's the only thing I based it on. I'm going to put it in there. But there's a different way you could have done this. Some of you have already shown me different ways that you've done it. Now that I have an expression for friction, I'm going to take that expression and use it up here. So f cosine theta minus mu times f sine theta plus mg cosine theta minus mg sine theta equals 0. Now, that was a lot of substitution. And this looks terrible. I mean, it looks like a nightmare. But if you look closely at it, it has f in it in 2 places. Everything else that's there is allowed to be in my answer. Now, just so you guys know, if you had set the coordinate system up to be aligned with f and the weight, this was a harder problem. It was easier to do this substitution because we aligned it up with things that could be eliminated. So in the future, as a hint, if you know you're going to have to eliminate something, if you know you can't have normal force in your answer, and you know you can't have friction in your answer, try and put them on an axis. It'll make them easier to eliminate. Otherwise, we'll get the same answer if you change your coordinate system, but it will be a harder algebra work for you. Even now, I know some of you are right at the limits of what you are capable of comprehending here, but we have to get f by itself, and I have seen some weird math in the last couple days. Really weird math. Like, how the heck are you gonna do this? So, understanding algebra, I know is a lot, and I also understand that I'm supposed to accept the fact that there might be a gap in your knowledge, blah, 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 COVID. I don't care. You've made it here now. Let's get together on this. The rules are pretty simple. I know some of you have to actually do the whole thing. Like, you have to write plus mg sine theta on both sides because that's the way your brain works, and you haven't evolved from there. So that makes these kinds of things take longer. I understand that. So take longer. Use a lot of paper. I don't have to do that, so I'm probably unlikely to. I am likely to do a couple of steps at once, but I'm trying to be patient, so I'm gonna probably write more steps out than I want. I just distributed the mu. Is that okay? I'm now gonna distribute the negative sign. I don't want to forget to do that. I now have 2 terms that have f in them and 1 term that does not. I'm going to take the 1 term that does not and move it to the other side of the equation. Because I've had algebra 2, I know about being able to use the distributive property to solve for a single variable. Again, this is a lot of algebra, and I am definitely going slowly and diplomatically, and all this talking I'm doing right now is filler for all of you who are trying to write things down. So, pretty close to the end here. I'm gonna divide both sides. That's the answer. How do you know? You don't. In this case, looks like a mess, doesn't it? It's hard to know whether that's even close to right. There are pieces in here that kind of make some sense, but it's hard to make heads or tails of what's been put here. There's also some weird stuff here. I will tell you that you should worry anytime there's a negative sign in the denominator. not for reasons that not for reasons that you're aware of yet, but that negative sign points to something that could be a problem. So let's handle some of the things that you could do to help you realize whether this is the right answer or not. Because I promise you, this problem, I didn't make this up. This has been on the AP exam. And this would just be like part 1 or 2 of a multi-part problem. So, oh yeah. And you remember 15 minutes per FRQ? This kind of work is probably being expected to be about 5 to 7. There's other things that have to happen here. But you're worried. You've done this for a week. When you've done this for a month, do you think it's going to take you as long as it took you the first week? All right, so just, be careful. It's just the beginning. There are some things here you can do to help you realize if it's the right answer or not. It's little stuff. Do you notice that there's something that can be factored out on top? Do you see a common term in both terms of the numerator? No, the mu is only on one term in the numerator, but mg is in both terms in the numerator. Do you see it? So that can be factored out. Part of the reason I'm doing this is to help you find ways to see if you're even on the right track or not. Everything in here is unitless. There's no units for any of those. Mu is a percentage, and sine of an angle is just a percentage as well. So there's no units in there. So the only things with units are these two things. They're the weight of the object, and that's going to be in newtons, isn't it? M times G has to be in newtons. I'm looking for a force, which also should be in newtons. So my units work out. That's usually a really good sign that you've done your algebra correctly and you haven't made some weird mistake by they work out here. The other thing, and this is what I will encourage you to pay attention to, this negative sign allows for an infinite result, right? Cosine theta cannot equal mu sine theta. If they do, it takes infinite force to push the box up. Right? Do you see what that's saying? There is a possibility where there is no force that can push the box up the ramp, and it's whatever would put those two things being equal. I'm saying this because if you want a 5 on the AP exam, this gets you to a 4. But the next question is going to be, what is one possibility that would prevent you from pushing the block up the ramp? And you'd have to recognize this is it. That getting a 0 in the denominator is an impossible circumstance. So what does that mean? Well, it looks like when mu equals cosine theta over sine theta, you got trouble. All right, that's what that means. So if that happens, there's no force that will push that block up the ramp. That's telling you not a single angle or a single mu. It's telling you a combination of things. By the way, cosine over sine, does it have a name? Cotangent, yeah. So I would probably just write it 1 over tangent, but it's cotangent. All right, so in my brain, if I wanted to assign credit, you know that I feel like everybody who is acclimating should have gotten to there without difficulty. Because this is our force concept inventory. It's what our series of steps have been about. A little bit of this is knowledge and experience and practice. A little bit of this, though, is also skill at algebra. That's going to be tough. Finding those kind of conditions is difficult. All right. This question was on the AP exam, not stated like this. They gave a picture, and the picture looks something like this, I think. It's been a long time. Something like that. And I don't remember from the question, so let me check. So this is where theta is, and it's a box of mass m. We want an expression for the tension in the right cable in terms of theta and m and fundamental constants. Okay? Don't think this should be a problem. Sounds like, though, we're going to have tension in the left cable will be a part of our problem, though, but it can't be in our answer. So I'm going to go ahead and list m, theta, and g. Those are likely the things that will be in my answer. Nothing else. Ready to begin? Free body diagram. So I'm trying to be a little careful here. I'm noticing that TL is the only one that provides an upward force. So I'm trying to draw it in such a way that this portion of the force is the same size or so as this portion of the force. So that it looks at least partially representative, and I think it needs to be a little bit longer to do that. And that means this one's gonna have to be pretty long. So this is gonna be TR, this is MG, and this is TL. All good? I'm gonna choose a coordinate system that is aligned with the weight, because that'll also be aligned with TR. By the way, this is, to me, a level 1 problem. It's very prescriptive. This is where theta goes. I'm using the alternate interior angles as my means of figuring that out. I just drew a line there and there and made the comparison that if this is theta, that has to be theta. So I'm going to break TL into its components. So TL cosine theta and TL sine theta. All good? I see one upward force and one downward force, and I see one left force and one right force. So net force in the x direction equals 0, TR minus TL cosine theta equals 0. And net force in the y direction is still sums to be 0, so that's going to be TL sine theta minus mg equals 0. We have to eliminate TL. There's a variety of ways you can do that. Substitution is one. I'm going to show you a different way. Since TL sine theta and TL cosine theta appear in the same problem, I'm going to solve for TL sine theta and solve for TL cosine theta. This allows for me to eliminate TL and leave the angle in there. So I'm going to divide both of these equations. On the right, that just gives me tangent theta. On the left, that gives me mg over TR. Any question there? All right. So TR equals mg over tangent theta. Interesting thing about that. What's tangent of 90 degrees? Try it. You got a calculator. I'm not trying to make this tough. You can't do tangent of 90 degrees. That's right. It goes to infinity, right? That's why tangent has that look to it. So at 90 degrees, TR is 0. Does that make any sense at all? It should, because at 90 degrees, that means the box is just hanging from the one string. No other string is necessary, right? So that tests. But also, it also tells me that there can't be 0 degrees on the string, meaning I can't pull on the string hard enough to make the whole thing just in one line. Because tangent of 0 degrees is 0. That would require infinite tension to do that. So this is why all wires sag under any circumstance. They have to. There's no way for any wire supporting any weight to be perfectly horizontal. This is the reason why. All right. This has been on multiple choice before. This analysis is not particularly long, but not terrible. That's a good one. This yesterday, and I'm making this up partially. I saw somebody do this yesterday. Multiple people in every class. This is wrong. This is bad math, bad. Some of you don't know why. And I can tell by the look on your eyes you don't know why. But it's okay. I'll explain why it's bad. When you divide both sides by cosine theta, every term has to be divided by cosine theta. You can't just pick and choose where you want to put that term. So you understand that if you believe that's possible, dividing and forgetting a term. If you do that, your units probably won't work out later on down the road.